IoT Sensors is a development app for visualization of sensor data. It supports temperature, pressure, humidity, air resistance, ambient light, accelerometer, impact, control of LED, compass with 2D and 3D calibration, gravity, gyroscope, battery, state of charge. The format used for sensor data is based on JSON. There are certain examples of all supported sensors below this document. Then for connectivity we have BOE, TCP and UART. There is also an option to bridge TCP to BOE or to UART, and this can be achieved using some compatible servers like gRelay or GNCOM, where gRelay is a relay server which connects multiple clients and allows the clients to exchange messages. When one client sends a message, this message is distributed to the rest of the clients. GNCOM is pretty much the same, but it also connects a UART to the group of clients. So data travels between the UART and the rest of the clients. And some examples of devices that I'm going to demonstrate now are Thingy91 and self-driving robot car. Let's start with the car, and let's start by launching the application. The first user experience, when started, the application will ask for BOE access, and once this is allowed, it will search for supported peripherals, and by default here it is configured to connect to NRF board from the car. The connection is established from the settings button. We have a field to enter BOE name and IP address. There is also a list of last used devices and a list of IP addresses and ports. And we can connect to either BOE or TCP, or we can bridge both of them, which means that when data arrives from one interface, it is forwarded to the other and vice versa. And this is very powerful when you introduce the relay server, and then you can connect multiple applications. Let's say we have sensors running on this laptop and then on an iPhone, and then you have another application that controls the robot car. It can connect and control the car as well. Anyway, let's look at the features. Here is our robot car, and I'm going to start by demonstrating the relay agent. Let's navigate to http://storm.com, then tools, gRelay. There is a version for pretty much any operating system. We are on a Mac. Download gRelay. It also supports WebSocket. There is a video demo on YouTube, but let's focus on our main application. I have already downloaded it. I then start it. Also connect Netcat. The default listening port is 81. Then go to IoT sensors, and we can bridge the BOE with TCP, and now we can see the data from our sensors. We can also enable logging, which will print the same messages, and we can send messages from the terminal, like stop the trace, or we can send messages from the IoT sensors application. For example, if I click the compass, it will tell the car, hey, give me compass data, and the car will replay with heading, with XYZ gravity. And now if we rotate the car, let me bring the video. So now if we rotate the car, compass will respond, and if we tilt the car, then the gravity will respond. There is internal compensation inside the car for tilt correction. If we disable it, then it's a different thing. The compass is now affected by tilt. That's why by default it is enabled. And now it's not affected. We have a nice trace. The trace, you can hold it to look around of the data that is collected. And you can turn off individual components. We can also reset, and then we start with a fresh trace. If it overflows, it will start from the beginning. Then for this particular set of sensors, we also have some buttons to calibrate compass. In calibration mode, it will provide some raw information from the magnetometer, and there are 4 steps for 3D calibration. The first step is rotate horizontally on a flat surface. You can see a progress. If the surface is not flat, it will warn to reduce the XY tilt. Then we can continue. And once we are past the full progress, that part of the calibration is done, we are asked to proceed with vertical calibration. And if we were doing a 2D calibration by pressing the 2D button before calibrate, then at this point the calibration would be over. And just as a quick demo, we can use that. It says X0, it's pretty much 0, and then if we tilt the car, now there is a progress. We need to make it as small as possible, which is a bit hard, but okay, that's it. And now we have minimal and so on. And if we want to cancel, we can press load to load the existing calibration. There is also a default button to erase the calibration in the car. 2D, 3D calibration, compensation, and magnetic or true north. And we can also use heading modes, which is shorter trace, uses less data, less bandwidth, provides only heading. Other than that, it's just a normal compass. Then another feature is the UART. We can connect the orange box, then go to settings, and from here select UART path, then connect. Now, since the board is charging, it blinks. Oh, by the way, the firmware is available here. Sensor firmware is the full address. So if you program this on a thingy board, then it will be fully compatible with the sensors application, the IoT sensors. This firmware and this board provides temperature, pressure, humidity, and resistance, light, infrared or RGB, accelerometer, and LED control. We can also connect to the board using BOE. If I change back to BOE peripheral name and select thingy 91, connect. We no longer need any cables. It should connect in a moment. And if you look here, you can see the green state charging battery. When we connect over BOE with the cable disconnected, this should change to a regular battery, not charging. For some reason the Mac is taking way longer sometimes to connect to BOE compared to an iPhone, which takes like no more than 2, 3, 5 seconds at worst. But the MacBook might take longer, like 20. Maybe Apple can look into this. Anyway, we're connected. And some other features, there is a push button in the middle of the N, which toggles the blue LED. Then at the bottom we have 3 LEDs, and right here we have another 3. And now the battery is 83%, 3.92 discharging. Now, if you would like to test the application manually without having access to some of these sensors, this is also possible. Let me disconnect from thingy. And I'm going to connect to TCP only. And now you can see if I try to enable the red LED, this is output 0 state 1 or output 0 state 0. Or I can also send a message from Netcat and say GPIO 5 is in state 1. There. Or I can say the state of all GPIOs are this. So 3F, everything is on. or all LEDs are off, and so on. Then we can send some data from the accelerometer, and it should react by updating the accelerometer graph. Let's force a low battery condition. And now the battery is red. We can also send compass data. And now the UI changes to compass with gravity, because that's what we sent. If we send compass only heading without any gravity, then the gravity data will disappear again, and so on. There are other sensors like gravity only, gyroscope, these are for compass calibration, inclination and declination, and so on, and battery configuration. There are also some row sensors. This is accelerometer with gyroscope. Then we also have support for raw magnetometer. And another good example for the bridge mode, if I connect again to the car and bridge, all right, we are connected. Now let's say we want another instance of our IoT sensor application. Could be on another laptop, could be on a phone. There it is. And this one is connected only to localhost, the TCP connection, and receives data from here. You can see they both work identically. Let's use an iPhone simulator. This might take a while. Or this is the application for control of the robot car. You can see it also shows the trace. You can stop this and then tell the car to navigate. And it is receiving the data from TCP and from the IoT sensors application. If we disconnect by pressing on the connection status, then no other data is received until we reconnect. So we can connect multiple clients. Each of the clients can send commands to control a device or receive data from it. It's really a nice set of features. And that's it. I hope the demo is good.